Hello. In this video, I will explain the physics behind the motion of an object falling with constant acceleration and demonstrate it with a real-life experiment and the computational model. In the computational model, along with weight force, I will model with and without the drag force. Later, we will be looking at the differences between the three models and extend our discussion to hypothetical questions. Let's go. This is the distance formula. Distance is equal to average velocity multiplied into time. And this is Newton's second law. If we do a little algebra, the law looks like this. If we incorporate Newton's second law into the distance formula, the distance formula will finally look like this. We will be assuming that only two forces will be acting on our object. One, which is a gravitational force and is represented by minus mg. Since the object is moving through the air, there's also another force to account for. This is called the air resistance or the drag force. This is proportional to the velocity square and is always opposite to the object's motion's direction. Here, we have our experiment set up in Tracker. I use a crumpled paper ball to impart a decent amount of drag. The mass of it is 10 grams. I've set the conventional direction for the axis, the side above being positive y-axis and the side below being negative x-axis. I drop it from a height of 2 meters. We treat the object as a point object and track its center of mass position for each time interval. The object is moving in the negative y direction. Now remember, this experiment is happening in the real world, and even though gravity is the obvious force, there's also another force acting in the opposite direction of the ball's motion. As we discussed, this is called the drag force and is pointing upward in this case. I will be using a computer simulation to replicate a similar situation of free falling. First, we will be assuming the net force is only caused by gravity and we will be neglecting drag. The code will iterate for every 0.001 seconds and update the velocity and position each time until the time reaches 0.655 seconds, which is the time the ball hits the ground in the real-life experiment. The orange arrow is a gravitational force, and since the acceleration is constant, you can see a parabolic position graph and a linear velocity graph. Next, we will be doing the same simulation, now including the drag force. I have set the constant b as 0.002. I got this number by trial and error, till the computer model matched my observational model. Here, you can see the arrow of the drag slowly increasing. This is because the velocity is increasing as the ball falls, and drag is proportional to the velocity squared. Position graph is still parabolic, but the velocity graph is not so linear anymore. It becomes concave as it approaches the end. Here is the graph when I plot a position versus time graph of all the three models. The red line is a computer model's position without drag, the yellow line is a computer model with drag, and the blue dotted line is the experiment's position. First, let's compare the computer model without drag and our observational model, the red and the blue lines. If we look at the ends, the computer line is clearly longer than the tracker model. This shows that without drag, the opposing force, the ball has traveled down longer in the given time interval. Now let's compare the computer model with drag and the computer model without drag, the red and the yellow lines. Both the lines run simultaneously up to a point. After reaching a point, the ball acquires significant velocity, which makes the drag force apparent. This reduces the ball's velocity and ultimately its final position. The difference you see between the red and the yellow line is caused by drag. You may have noticed that there is a slight difference between the experimental observations and the computer model. The difference might be due to human error while marking the center of mass. Since the ball was moving very fast, it was blurry and I had to approximate the center of mass. These approximations might have caused a slight difference. Now let's extend our discussion to some questions. What's terminal velocity? Terminal velocity is the constant velocity the ball reaches due to the gravitational force and the drag force being equal and opposite and eventually canceling each other out. If we look at the model with drag, notice here how the position graph stops being parabolic and starts being linear. This is because the velocity somewhat stopped increasing at this point due to a large enough drag force in the opposite direction. What happens if I throw the ball downwards with some initial velocity? Let's test it out. In all our previous cases, initial velocity was 0 since I simply dropped the ball. Now let's impart some initial velocity to it and run the program. As you can see, the drag and the force are equal and opposite in direction and eventually get cancelled out. The length of the arrows are same. And the velocity graph is a concave graph, and the velocity is about to become constant, which is also known as the terminal velocity. Thank you for watching. Links to my works will be in the description.